So today's announcements, the sapling grading policy, I think we've got it fixed, but the points that were deducted for early tries, it sounds like they're going to retroactively apply after the due date closes. So that should sort it out. Everyone who completes the assignment, in other words, will get 10 out of 10. Okay, also Recitation Quiz number 1 is next week, and it's going to cover, as all the recitation quizzes will, up through the end of Friday the week before, so end of today's lecture, wherever we get to, that's going to be the cutoff point for the quiz. Also, just a reminder, if you missed lecture on Wednesday, I included some more guidance on Canvas about what to do on Packback, but make sure you get 3 contributions on there by Sunday night, or earlier, hopefully, so that people can actually get a chance to comment on them. Okay, questions about any of that? Yeah. Mm-hmm. Yeah. Correct, yeah. Chapter 14 sapling will not be due until a week after we finish Chapter 14, which will likely be, I was aiming for today, but I probably won't finish the whole chapter today, so a little bit into Monday is where I'm going to sort of finish that up, and so that'll be due Monday the following week. Okay, other questions about that? Okay, cool. Alrighty, so where we left off was looking at oxidation of alkynes. So we covered sort of a generic outcome where you make an enol no matter which route you're going through, and then that enol, as soon as it forms, will immediately rearrange to the keto form. So hydration of alkynes. Which includes ketoenol tautomerism or ketoenol tautomerization, depending on which book you're going. I forget which one Loudon calls it. But it's the same thing. It's just going back and forth between 2 tautomers. Okay, so we looked at the acid-catalyzed hydration. As a heads up there, so I kind of left mercury out of the mechanism entirely, and the book includes it. The book is also a little bit kind of waffly on exactly how the mechanism works. They're like, here's mercury attached to the alkene. Maybe it makes a 3-membered ring, maybe it doesn't. No one knows for sure. There's a lot more going on in the mechanism than what I covered, and I kind of decided not to get bogged down in the details. So if you have questions about it, we can talk about it later, but I'm not going to be testing on that one because, to be honest, there's a lot of parts where just no one is real sure exactly what's going on for sure. So I just kind of covered that as like, if it's analogous to alkene acid catalyzed hydration, here's what happens. But yeah, there's a lot going on there. But in the interest of pushing on and getting to more interesting stuff, I'm just going to totally gloss that over and go on to the next one. So hydroboration oxidation is what we're going to look at today to start off. Okay, so this one, if you remember from alkene chemistry, this is going to add an H and an OH, so it's another hydration mechanism, but it's doing it anti-Markovnikov. Okay, so just like we did for alkenes, we can add some kind of thing that has a boron attached to an H. So BH3 or BH3.THF or B2H6. These all work okay for this. The problem is they're not as selective for anti-Markovnikov regiochemistry, so they're going to give you a fair bit of the Markovnikov product mixed in. And that's just because the alkyne doesn't have as big a difference between the more and the less substituted side, which sort of makes sense. Like on the alkene, you had a fair bit of sterics going on with like stuff getting in the way. Alkyne is a little bit more like streamlined looking. So when people started trying to do this chemistry on alkynes, they realized our cell activity here is not great. We're getting a bunch of byproducts, the Markovnikov addition stuff mixed in. So what they decided to come up with is a version of BH3 that has a bunch of sterics of its own, so it's going to have to be a lot more picky about where it adds. So instead, they're like, let's just take BH3, let it keep one of its H's so it can do the addition onto the alkyne, like it does to the alkene, and then just cram a whole bunch of branchy alkyl groups on there. So that's what they did. They put 2 of these groups on here. Okay, so it's basically a couple of tertiary carbons stuck together, and then one of them is linked to the boron in each side. Okay, so this group has an IUPAC name if you want to go through and figure it out, but it also has an older non-systematic name that we haven't seen. This, as it turns out, is called cyamyl. Amyl is a really old name for pentyl, which if you count, these each have 5 carbons, 1, 2, 3, 4, 5. So Cy is some weird prefix. I don't know if it is like generally applicable to other groups, but at least like this particular arrangement of 5 carbons is called the cyamyl group. So this boron is still going to do the same kind of addition mechanism that BH3 did to alkenes, only it's going to have a lot better pickiness over which side it adds to. So, oh, and by the way, you can also write this as, I don't remember if I include this in the notes anywhere. It looks like I don't, but BH Cia2 is another way you can write that, or you can reorder it like HB Cia2 or Cia2BH. But it all works out to the same thing. In the book, they also show it written on the arrow as like this weird blocky linear version of the group, but it's still also the same thing. Okay, so if you show the mechanism for this, it's arrow for arrow exactly the same thing that we did. I'm not going to draw it out. I'll just say a couple of Cia groups on there. It's the same mechanism that we showed for alkenes, where the pi bond goes out because it's nucleophilic. It's going to go out and attack. And what it's attacking is this empty orbital on the boron. So that's the electrophilic site on the boron here. And then meanwhile, to prevent a carbocation from ever forming during this mechanism, some electrons are going to come from here and attack back onto the alkyne. And the only electrons that this thing has to spare are the electrons out of its sigma bonds. Turns out the BH bond is the easier one to break. And so the H just sort of picks up its electrons out of that bond and hops over onto the carbon. So you end up at boron attaches to the less substituted carbon, and hydrogen attaches to the more substituted carbon. So in terms of why the regiochemistry works out this way, partly it's due to sterics, like those cyamyl groups want to stay away from whatever other R group is on here. And partly it's also due to electronics, where even though you never actually form a carbocation, you do start developing a little bit of delta positive charge on whichever end is better equipped to handle it, and then that's the one the hydrogen ends up joining. Okay, and then from here, this is where we throw in the reagents for step 2, which I don't know which other OChem 1 professors cover the mechanism for it. I didn't though, so I'm just like showing the reagents here, and you don't have to show how it works for this step. If you're curious about that, it is covered in the study guide though, back in like chapter 5 when they covered it for alkenes. It's kind of a cool mechanism. It's like a carbocation rearrangement, but not quite. Okay, so that gets us to here. That is an enol. And so immediately once that forms, it's going to tautomerize. All right, so given that we happen to be in base when this enol develops, it makes sense that out of the two mechanisms we covered for tautomerization, it would have to go through the base catalyzed mechanism just because that happens to be the circumstances in which it finds itself. So I'm not going to write out the whole mechanism for that again, but this is where you can take that base catalyzed tautomerism, plug it into this if you wanted to show like as close to a full mechanism as you can get, given that we kind of gloss over this step too. Okay, so that gets you to here. If you want, you can show the H's off of there as well. Okay, one thing you might be asking is, during this step, I've added the boron onto here. I still have a pi bond though, so what's to stop another molecule of dicyamylborane from coming in and adding onto here and getting two borons coming off and just a carbon-carbon single bond? This is another reason why we really like using this bulky boron for this step. It's because this thing takes up so much space that there's just not enough room for another boron to get in here. So this is too bulky to allow a second addition. So it's pretty much, even though it is sitting around with a second pi bond sort of that could possibly react, it's very unlikely that you would ever see two borons coming off of the same carbon there. It kind of blocks off any chance of a second addition. Okay, so again, kind of like the stuff we covered last lecture, it's real similar to things that we've seen before, but there's some added wrinkles just because there's now two pi bonds instead of the one. Okay, questions about that reaction? Alrighty, cool. Okay, so we've covered HX addition. We've covered, oh, sorry, question? Yeah, sorry, that's right.
If we were asked to show this mechanism on a test, would you want us to show the tautomerization as well, or should we just leave it?
So I would have to specify exactly what I want. Yeah, I guess like if I didn't say, then you'd probably be okay to just show the first step, but yeah, unless I wanted like a whole bunch of regrade requests, I would have to be pretty specific on what I was expecting there. Yeah. Okay. Other questions about this one? All right, cool. So we covered HX addition, we covered hydration. Now we're going to move on to a third category of stuff that we did to alkenes. And again, we got multiple ways it can happen now. So instead of hydration, we're looking at reduction or hydrogenation. So if you guys remember, I guess when we covered redox chemistry, or at least we did in my lecture, hopefully that sort of rings a bell for people in other lectures. It's in my chapter 10, 11? 10 chapter notes if you're feeling a little bit rusty on it though. So reduction just means we're adding two atoms that are both less electronegative than carbon to the molecule. So pretty much the only example we saw of that as a final product was two H's getting added. So that's what we're going to be doing here. So we're actually going to see three reactions that fall under this category. If we just hit it with the same stuff that we did for alkanes, it's going to end up going to the same point as same stuff we use for alkenes. It's going to go to the same point. So if we do it with palladium or platinum, we're going to, and for this one I am actually going to use internal alkynes so that we can see what happens to the R groups relative to each other. because here the stereochem turns out to be pretty important. And we don't have to pay attention to regiochem because we're just adding two H's. Okay, so we've got our alkyne here, and we're just going to use H2 and PD on C, just like we used to hydrogenate an alkene. Turns out we can't stop this thing. It's going to add to both pi bonds before we can get a hold of it and stop it part way. So ultimately where we're going is adding two equivalents of hydrogen. You might be wondering, if I use one equivalent of hydrogen, could I get it to stop part way? Turns out that's really tough for practical reasons, like hydrogen being a gas. You have to pressurize the whole thing with a lot of hydrogen to make it go. So there's no real good way to stop it after one addition. Plus there's the added complication that as soon as you get one equivalent added on there, the alkene that you make is actually more reactive to this and is likely to go through all the way to the end. So pretty much if you use the chemistry that we used before, it's just going all the way to the alkane, which sometimes is what you're going for, but sometimes it's not. So if we do want to stop this part way, we're going to have to set it up differently. So what we're going to use instead of just straight palladium or platinum is something called Lindlar's catalyst. And what this is a similar catalyst to palladium or platinum, just it's being what they call poisoned by adding in some other stuff to it. There's a few different things you can add. I think like the one that Lindlar himself actually developed had some lead salts in it. It was still mostly palladium or platinum. Or there's some similar, or ones with similar behavior that weren't technically Lindlar's original thing, but they kind of get lumped into the same category in description, which you can poison with some organic stuff. Pyridine, which came up a little bit in OChem 1, or quinoline, which is similar. Basically just some nitrogen-containing stuff. So it turns out what these do is they don't hinder the reaction with the alkyne, but they do hinder the reaction with the alkene that you form at the halfway mark. So you start with an alkyne, you add H2, and you would just write on the arrow Lindlar or Lindlar's catalyst. Just writing H2 and Lindlar is fine, although that kind of looks like you're throwing the actual chemist guy himself into the reaction, but you're not. Okay, so this is going to add one equivalent of hydrogen to the molecule, and then it stops.
Do you have to specify one equivalent on the arrow, or is that implied?
So you can actually use like a whole bunch of hydrogen and it doesn't matter. It's still going to just stop part way because the catalyst itself is kind of the bottleneck for this thing. So yeah, pretty much anytime you have a gas as a reagent, it's going to be fairly hard to sort of tweak the number of equivalents you have unless it's like very soluble in something like HBr you can sort of play with because you can get it soluble in water, but like H2 is just, I don't know if there's any good way to do that. So, okay, other questions about this one? Okay, so one thing you might be noticing is the stereochemistry on this. I'm showing both H's pointing in the same direction. Every time you do a hydrogenation, so I sort of put like a little cartoony, like partial mechanism when I covered hydrogenation for alkenes in OChem 1. But the gist of it is that both H's kind of click onto the molecule at the same time from the same direction. And so doing any sort of hydrogenation with a solid catalyst and hydrogen gas will always give you syn addition, where the groups end up cis to each other. So long story short, if you're doing a hydrogenation with Lindlar's catalyst, you will always get the cis alkene from the alkyne. So this is via the syn addition of the hydrogens. Okay. So questions about that one? Alrighty, cool. So then you might be asking, okay, we've got one alkene out of this. Can we get the trans alkene going instead? Turns out, yes, you can, but you can't do it by solid catalyst and hydrogen gas. We actually need a totally different way of doing this, which is why I sort of left this category at the top of the board a little bit vague. It's reductions, of which some are hydrogenations and some are something else. Okay, so what we're looking at here is a totally new type of reaction. It actually has more in common with organometallic chemistry than with hydrogenation and alkene chemistry. So this is reduction with sodium metal and liquid ammonia. Another name for this is a dissolving metal reduction, because that's actually exactly what happens. Can you guys see at the front? This chair's getting in the way. Okay. That's not going to work. Okay. So, it's called a dissolving metal reduction because that's exactly what happens. You start out with a chunk of sodium metal in there, and as the reaction proceeds, it actually turns into sodium salt, which dissolves and disappears. So again, you start out with an alkyne, and the way you would write it here is Na, and then NH3 liquid. And this will give you the trans alkene. From anti-addition of hydrogens. Okay. So, we're going to actually go through the mechanism for this. And this is the first time we're going to see sort of radical single electron stuff and charges going on at the same time. Oh, gotta move the camera. Okay. So another name for this reaction is Birch Reduction. So you might see any or all of those names attached to it. Okay, so mechanism, it helps to keep things straight if you think of it in 4 separate steps. First, we're going to add an electron from the metal, then we're going to add a proton from the ammonia, and then we're going to do both of those steps again. So add an electron, add a proton, add an electron, add a proton. Okay. As a reminder, in terms of organometallic species, which we turn out to be forming during this, so say we're looking at organolithiums that we're a little bit more used to seeing here. So we can show this as a covalent bond between the carbon and the lithium, or we can show it as something with a negative charge here and a positive charge on lithium. So the real structure is somewhere midway between them, depending on exactly which metal it is and what the R group is, but either one of these depictions is a valid way to show an organometallic gesundheit. Okay, so the mechanism for this is, let's say we're using this again. I'm just kind of drawing a bracket around that thing. All right. So remember that sodium metal, not sodium salt like we're used to seeing it as an Na+, straight up sodium metal in its neutral form, based on where it is on the periodic table, has a single electron on it. And so what we're going to show is this thing coming in and doing something that we've seen before in radical reactions, where you've got like a single electron radical bearing thing comes in, contributes one electron to a bond, and then a pi bond's going to break, contribute the other electron to forming that bond, and then the leftover electron falls back onto the other part of the pi bond, the other carbon in this case. So that gets us to something that looks like this, where you've now got a radical here, and you've got a bond to sodium, which you could just as easily show as this thing. All right, so this is the first time we're seeing charges and radicals going on at once. But it's still following all the same electron pushing rules we're used to seeing. It's just we're getting to kind of a weird place with it as a result. Okay. So, and I guess if I want to balance things, sodium plus is still nearby. Okay, so then at this point, we need to add a proton. It makes sense to add it to the place where there's a negative charge. If you go through and look at the pKa values of this, this is still like quite a strong base, pK probably in the mid-40s. Question? So that's an excellent question. I'm actually leaving it vague for now because it turns out it can go back and forth a bit, but I'll talk about that afterwards. So right now, I'm just going to focus on the connectivity, and then we can go back and look at why do things turn out the way they do. Yep. Sorry, where? Oh, there you are. Okay, sorry, yeah. Mm-hmm.
If this was like if there were like different substitutions on each side,
Mm-hmm. The radical is going to be most stable on the more substituted side. So I guess like if you had like a CH3 and an H, it would be most comfortable close to the CH3. And anions are also most stable like furthest away from the R groups, so they're best on the less substituted carbons. So yeah, it would pretty much follow the rules that we've seen for like radical stability, and then the negative charge ends up being pretty happy with how things work out for that too. Okay. All right, so at this point we got to add a proton. I guess, yeah, let me actually go ahead and get into the stereochemistry aspect of things here too. So it turns out that once you have a lone pair on something, you can actually sort of, I guess the geometry around that atom is not locked in place. The lone pair can sort of pop out the other side of the carbon atom, in other words. So So the anion form here can flip its stereochemistry so that it can go back and forth between these two versions. And that just comes down to lone pairs being kind of squishier, I guess, than R groups, where they're not as locked in place and can sort of flip the stereochem at will. And I don't remember if we covered this in the stereochem chapter, where like if you've got a lone pair on nitrogen, it can do the same thing and just invert the stereochem at the nitrogen so frequently that we don't consider nitrogens to be chiral if they've just got 3 R groups. Okay, so while it's in this form, it's sort of flipping its R groups back and forth all over the place because it can invert them just sort of at random. But based on what we know of alkene stability, which form, like the cis-like form or the trans-like form, is likely to be more stable? Trans, right? And so this form is where it ends up spending most of its time. Like it'll spend some of its time in the cis form. So I'm kind of leaving it vague on stereochemistry here, but I think it was Niketna who asked the question, but yeah, you're totally right. Most of the time it is actually going to be, how do I have it in the notes? Okay, so I'm going to flip this methyl group up just to get it to be trans here. Okay. So it is still going to spend some of its time in the cis form, which means we are going to get like some of the byproduct where it has the wrong stereochemistry. But most of the time trans is going to be the way that it's looking while it's sitting around in this form. And so when the next step happens, it's going to go pull an H off of the ammonia. And then get to here. Okay. So at this point, we need to add one more electron, add one more proton, and we're going to do those the same as we did before. So sodium here. So now this is looking a little bit less like kind of radical propagation steps that we saw in OChem 1, and a little bit more like a termination step from a radical mechanism. You've got 2 separate things, each with an unpaired electron. So let's just stick them together and have them terminate the radical sequence, or radical kind of properties. Okay, so you get to here, which again, you could just as easily draw as this. And again, this has the same flipping its stereochemistry freely kind of deal going on that this anion had over here. So this thing can sort of choose between cis and trans, and most of the time it's going to pick trans because that's more stable. And so then to finish it up, it's going to take the NH2, take the H off of NH3 and get to here. Okay, so the electronic situation in this molecule looks a little bit weird in some of the steps, but it really is very similar to bits and pieces of mechanisms we've seen before, just we're putting them together in weird ways. We're combining radical and acid-base chemistry. Okay, so questions about, yeah. Mm-hmm.
I could be wrong, but I was under the impression that you can't really rotate around the double bonds. And how
So it's not that you're spinning around the double bond, it's that this carbon itself, like, let me draw what's going on actually. Okay, so what's really happening here is, let me do this for like nitrogen real quick first. So say you've got like a nitrogen with 3 different alkyl groups in a lone pair. You look at that, you're like, there's 4 things on it, it's chiral, right? But the lone pair is kind of squidgy and doesn't stay put. So like you've got tetrahedral stereochemistry on the nitrogen, but it can sort of do this thing where temporarily you actually turn it into a p orbital, and this thing goes trig planar briefly, and then it pops out the other side of the nitrogen. And you sort of invert the stereochemistry on the nitrogen. Even though none of the R groups like came off or anything, it's just the lone pair sort of popped out the other side of the N and flipped the pyramid. It's sort of like what happens during an SN2 reaction, just there's no actual like attack or anything, it just happens on its own. And so the same thing's happening here. You're not like twisting the double bond, it's just this carbon is just going like the lone pairs are sort of popping out the other side and bending the R group up or down. So yeah, that's a really good question. It's sort of weird looking if you're expecting like alkene rules to be followed, but it turns out there's just something going on that individual carbon that is funny looking. So yeah. Okay, yeah.
So with the cis form of the alkene generated, wouldn't that give us a mix of a cis and trans?
Yeah, so for this, I'm usually just going to show the major product unless there's a really important reason to think about the minor product. But yeah, pretty much like every stereochemistry or regiochemistry like outcome that we're going to see is always going to be like that's the major product, but you probably get some of the opposite like thing mixed in as a minor product. So I guess our goal is to just minimize the amount of other stuff we're forming so that we don't have to clean it out by doing some kind of separations later on by recrystallizing it or whatever. Yeah, but none of this is like neat and 100% controllable. There's always going to be some issues that come up for outcome. We're just trying to minimize byproducts. Okay, yeah.
Does this not ever continue on to make the alkane?
So no, and I think the reason for that is because when you do it for the alkyne, you're getting a negative charge on an sp2 carbon. So the pKa on that is like mid-40s. If you went through this a second time, you'd be getting a negative charge on an sp3 carbon, pKa in the 60s. And I think that's just too strong a base to be allowable based on what else you have in there. I guess if you had some like super electropositive metal, maybe like way down in the bottom left of the periodic table, like francium or something, that's just like, take this electron, I don't want it. Maybe that would be enough to force it to happen like all the way to the alkane. But yeah, to be honest, I don't know for sure. That's just kind of, I don't know, educated guess, I guess. Yep. Yeah.
Do you have to deal with the explodiness of solid sodium?
You do, yes. It's actually not as big a deal. Like sodium, a lot of the time in the lab, you just have a chunk of sodium that's stored under mineral oil, and then you just like hold it with some tweezers and rinse it off with hexanes and add it to whatever reaction. So long as you're careful that the thing you're adding it to is not got any water in it, then you're usually okay. Yep, good question. Okay, other questions about this? Okay, cool. So that's kind of 3 different things you can do to reduce and or hydrogenate your alkyne. And depending on which one we're going for in a synthesis, we now have pretty good control over whether we make cis-alkene, trans-alkene, or whether we just ditch the pi bonds entirely and go to an alkane. Okay, so the next thing we're going to cover is actually changing gears quite a bit from what we've been doing so far. This is not analogous to anything that we saw for alkenes. This is some new stuff that's specific to alkynes. So I guess new chemistry might be a bit of a stretch because really all this is acid-base. We're just using it in a particular way that lets us access some cool stuff. So acetylides are what we're working with here. Okay, so basically, what we're going to do is take a terminal alkyne, one with an H hanging off the end, and we're going to hit it with a base. And we're going to rip that proton right off the end and get a negative charge on here. Okay, so based on what we know of pKa's, if you've got a pKa table handy, the pKa of this proton is going to be about mid-20s usually. So if we want to make sure this works, we need a base with a higher pKa. We actually have a bunch of options, but if we want to do it in a way that doesn't lead to other organic stuff floating around in our mixture and possibly causing problems, usually the best bet is this thing, sodium amide, NaNH2. because this thing has a pKa of somewhere in the mid-30s. I don't remember exactly. I want to say 36. Okay, so this is strong enough to pull off the alkynes proton and get us to here. All right, a word of warning. This is actually a salt. It's Na plus and NH2 minus. This is very, very different from Na, comma, NH3. So this is a metal and a neutral solvent. This is a strong base that's a salt. So if it helps to mentally split it up to like Na plus, NH2 minus, definitely go ahead and write that in. But make sure that you're keeping an eye out. Like they look really similar, but they're very different in behavior. Okay. So once we've pulled our proton off of the alkyne, we get to this. This, as it turns out, is still a strong base, just not as strong. It is also a pretty good nucleophile. So strong base, good nucleophile. Guess where I'm heading with this? So SN2 is what we can use this for. Okay, so what we can do is take some alkyl halide that's capable of having SN2 performed on it. I'll just use the best possible, or almost the best possible, alkyl halide for SN2. So like methyl bromide, you could react this with. Attack the CH3, kick out the halogen, and we just made a new carbon-carbon bond. So yeah, so this is sort of a second way that we have of sort of at will making carbon-carbon bonds. I guess you might be asking, why didn't we just do this with like alkyl lithiums or Grignards back when we covered them in chapter 9? The answer is that those are really strong bases and good nucleophiles. They're actually a little too strong a base. They're such strong bases that they will actually tilt towards E2 a lot of the time if there's any way for them to do E2. So these are kind of in the sweet spot of strong base, good nucleophile, but not such a strong base that they are too good for SN2. So these will come in, do a substitution onto the carbon and form a new bond. And so we can actually do like a lot of different varieties of putting together structures just based on exactly what we're going for. So especially if we start with an alkyne that has an H on both ends, so we can actually do these steps twice sequentially. Deprotonate, make it do SN2, and then deprotonate again, make it do SN2. We're only going to pull the H off of one side at a time, so we don't have to worry about double addition, which makes sense because, you know, it's very unlikely that you'd pull an H off of both sides at once and get something with two negative charges. That seems unlikely. So if we're starting with acetylene, which is the alkyne with two H's on it, we can do it for both ends one at a time. So for example, start out here, and you don't even have to write these out at separate steps. People are so used to doing these like one right after the other that you can just say step 1, NaNH2, step 2, whatever alkyl halide I want on there. Let's say butyl bromide. And that'll get us to, I sort of coiled it up in the notes just to keep it fitting on the page properly. But that'll get us to something with a new 4-carbon chain stuck onto the alkyne. And then we can do the same thing to the other end. Maybe let's use a different R group this time though. NaNH2. And then maybe isobutyl bromide. So this thing we could make. And then once we've used this alkyne as sort of our linchpin of the molecule to like stick one group onto one end and then another group onto the other and like hold the whole thing together, once we've done that and finished getting our carbon skeleton put together, then we can tweak the alkyne into whatever we want based on the stuff that we just finished covering. So we can maybe, I don't know, turn this into an alkene, for example, if we want to do like NH3, then we could maybe do a dissolving metal reduction and get to a transalkene, for example. So like that. Okay. So we're now adding to our extremely useful reactions thing in terms of being able to actually put together the framework of the molecule that we want, even if we're starting more or less from scratch over there with our alkyne. Yeah?
Would the beta branching of the isopropyl bromide cause E2?
It might tilt a little towards E2. The good news is it's not neopentyl. You don't have a quaternary carbon on here, so I'd say it's still probably going to favor SN2 as the major product. If you do want to tweak the outcome, you can actually like lower the temperature. It tends to favor substitution a little bit more, but yeah, you probably will get some byproduct, unfortunately. So, all right, I'm going to wrap up there, and then we can finish the chapter on Friday. Or Monday. Ha.
Decide whether